Now we're going to turn to general exponentials. So another class of functions, we've seen one specific example, the natural exponential, and more generally we're going to use the natural exponential to define the more general exponential of base a. So a here is a fixed number that is positive and different from 1. And then for any real number x, we can define a to the x using the natural exponential as e to the x ln of a. Of course, you can see that this should be what you expect, because this x ln of a, you can bring in the exponent and get e to the ln of a to the x, in other words, a to the x. So the defining formula here is a to the x means e to the x ln of a. And the function that to each x in the real line associates a to the x for a fixed a that is neither 1, that is not 1, and that is positive, this is called the exponential function of base a. Of course, the natural exponential is the case where a is the Euler number e. Now these exponential functions have pretty much the same kind of properties that we have seen for the natural exponential. In particular, the laws of exponents are satisfied for this more general kind of exponentials. If we have a to the x plus y, that's simply a to the x multiplied by a to the y. A to the x minus y is a to the x divided by a to the y. A to the x that we raise to the power y is a to the power xy. And one additional observation is that if I have a product of two numbers, say two positive numbers, a and b, and I raise that to the x, it's the same as taking a to the x and multiplying by b to the x. I'm not going to go over the proofs for each one of these, I'm just going to indicate why this follows immediately from the corresponding laws that we have seen for the natural exponential, just for the first one. So for the first one, we want to see that a to the x plus y is a to the x times a to the y. We go by the definition. A to the x plus y is e to the x plus y times ln of a, in other words, e to the x ln of a plus y ln of a. And we know that for the natural exponential of the sum is product of the exponential. So we get e to the x ln of a multiplied by e to the y ln of a, but by definition the first term is a to the x, the second one is a to the y. And so that proves the first law, because we've already proved it for the natural exponential. The others follow pretty much the same way from the properties of the natural exponential. So the important thing to remember is really the definition of this exponential of base a. A to the x is by definition e to the x ln of a. From that follows these laws of exponents, but just to illustrate the definition, for instance 2 to the pi, you should really think of that as e to the pi times ln of 2. Or an expression like 10 to the x squared, you should immediately rewrite that as e to the x squared ln of 10 if you have to do anything with it, like for instance differentiating. Talking about derivatives, we can ask the question, what is the derivative of this exponential function of base a? And again, we're just going to go back to the definition. A to the x is e to the x ln of a. So we have the function x ln of a plugged inside the natural exponential, and we know how to differentiate the natural exponential. Its derivative is itself. So we use the chain rule. We get the same exponential multiplied by the derivative of the function inside. So again, e to the x ln of a, and then we multiply by the derivative of x times ln of a, and that gives us just ln of a. The first term, the exponential, is really just another way of writing a to the x. So what we get is a to the x multiplied by ln of a. In other words, the derivative of the exponential of base a is itself multiplied by ln of a, where a is a base. Of course, the case where a is e, then we multiply by ln of e, and by definition ln of e is 1. So instead of having the derivative of the exponential function is exactly itself, we have to scale it by the natural logarithm of the base. In the case of the natural exponential, we get exactly the function itself. If we turn around the formula in terms of integral, an antiderivative of a to the x would be a to the x divided by ln of a, because if I differentiate this, differentiating a to the x is going to give me a to the x multiplied by ln of a, and I have to cancel out that. So now let's apply this formula for the derivative in particular to a few examples, starting with the function g of x defined by x to the fourth multiplied by 4 to the x. And let's say we want to differentiate that. So that's a product. We're going to use the product rule. We get derivative of the first factor multiplied by second factor unchanged plus first factor unchanged multiplied by derivative of the second factor. And to differentiate x to the fourth, so here we have x is in the base and we have a constant exponent 4, so this is a power of the variable. We use a power rule, we get 4x cubed, right? If you have x to the n, you differentiate, you get n x to the n minus 1, where n is a constant. So we get 4x cubed for the derivative of x to the fourth. On the other end, when we differentiate 4 to the x, we have a constant base and the variable in the exponent. This is an exponential function, in this case of base 4. We apply the formula we've just have seen, get the same exponential 4 to the x multiplied by the natural log of the base. So we obtain 4x cubed times 4 to the x plus x to the fourth times 4x multiplied by ln of 4. Now let's look at the second function of the variable theta, defined by 10 to the tangent of theta. Again, the first thing we're going to do is write out what that means. 10 to the tangent of theta is really e to the tangent of theta ln of 10. And we're differentiating this. So we are plugging the function tangent of theta times ln of 10 inside the natural exponential. So it's a composite, and we use a chain rule. We get the exponential, the derivative of the exponential evaluated at tangent theta ln of 10. And then we have to multiply by the derivative of the function inside. The first term, of course, is just 10 to the tangent of theta. And for the second term, I have a constant ln of 10 multiplied by the tangent function. Derivative of the tangent function is secant squared. Therefore, I get 10 to the tangent theta, corresponding to the first parenthesis. And then derivative of the second term is just ln of 10 times secant squared of theta. Now let's try to differentiate y equal x to the 1 over x. This is of a slightly different nature from the other two examples, because now I have the variable both in the base and in the exponent. Nevertheless, all we really need to know is again the definition of a power in terms of the natural log. Specifically, we can rewrite y as e to the 1 over x times ln of x. And once it is in this form, it's easy to differentiate because it's just a composite where we plug the function 1 over x times ln of x inside the natural exponential function. So we differentiate using the chain rule, get the derivative of the exponential, which is itself, evaluated at 1 over x ln of x, and then this is multiplied by the derivative of the function inside. So this 1 over x ln of x that remains to be differentiated, it's a product, so we can use the product rule. The first term is really just another way to write x to the 1 over x, and for the second term we use the product rule. Derivative of 1 over x is negative 1 over x squared. We multiply that by the second factor unchanged. Then we have 1 over x multiplied by derivative of ln of x, which is 1 over x. So we get 1 over x squared. We can factor out 1 over x squared. And we could also observe that if I have x to the a divided by x to the b is going to give me x to the a minus b. So here I have really x to the 1 over x minus 2, that is multiplied by 1 minus ln of x. Number 4 is again one of the situations where we have the variable x both in the exponent and in the base. Again, the one thing we need to remember is the definition of a power. A way around that would be to use logarithmic differentiation that we've discussed in the previous model. So here my function can be rewritten e to the x natural log of sine x. And again, I'm just plugging the function x natural log of sine x inside the natural exponential. It's a composite. I use a chain rule, and I get derivative of the exponential evaluated at the inner function x ln of sine x. And then I have to multiply by the derivative of this x ln of sine x. The first term, the exponential, is really just sine x to the x. And for the second one, I'm going to use the product rule because I multiply x by a natural log. So I get sine x to the x for the exponential, and then applying the product rule, derivative of x is 1, I multiply that by ln of sine x unchanged. And then I have x multiplied by the derivative of ln of sine x. We know that the derivative of ln of sine x, it's again the chain rule, because I'm plugging sine x inside the log. So I get derivative of the log evaluated at sine x, that's 1 over sine x, multiplied by the derivative of the function inside, so multiplied by cosine x. So I get x multiplied by cosine x over sine x.